Good day, ma'am. I am Chloe Bernasol, and today I will be discussing the topic of Pearson correlation, Spearman-Rank correlation, and Kramer's correlation. So the first topic I will discuss is the Pearson correlation. So what is the Pearson correlation coefficient? Pearson correlation coefficient or Pearson's correlation coefficient or Pearson's R is defined in statistics as the measurement of the strength of the relationship between two variables and their association with each other. In simple words, Pearson's correlation coefficient calculates the effect changes of in one variable when the other variable changes. For example, up till a certain age, in most cases, a child's height will keep increasing as his or her age increases. Of course, his or her growth depend upon various growth factors like genes, location, diet, lifestyle, and etc. This approach is based on covariance and thus the best method to measure the relationship between two variables. So what does the Pearson correlation coefficient test do? The Pearson coefficient correlation has a high statistical significance. It looks at the relationship between two variables. It seeks to draw a line through the data of two variables to show their relationship. The relationship of the variables is measured with the help Pearson correlation coefficient calculator. This linear relationship can be positive or negative. For example, positive linear relationship, in most cases, universally, the income of a person increases as his or her age increases. Negative linear relationship, if the vehicle increases its speed, the time taken to travel decreases, and vice versa. The formula for Pearson's correlation is R is equal to the sum of each value of x minus the mean of x s bar multiplied by the each value of y minus y bar the mean of y and divide that by the square root of the sum of each value of x minus the mean of x squared multiplied by the sum of each value of y minus the mean of y squared. I'll give you two examples of Pearson correlation and let us tackle first the one example. Now let us do an example of correlation coefficient. An agricultural research organization tested a particular chemical fertilizer to try to find out whether an increase in the amount of fertilizer used would lead to a corresponding increase in the food supply. Let's look at the data. Fertilizer in pounds and bushels of beans, and that's the data. Now we need to think about who's going to be X and who's going to be Y. In this case, the fertilizer is going to be X because that's independent on how many brand will be produced. So these will be X and these bushels will be Y. Y is called the dependent variable because it depends on the fertilizer. Now for the correlation coefficient, we're going to need more variables. We're going to need x times y. We're going to need x squared and also y squared. Now let's multiply x times y. So 2 times 4 is 8, 1 times 3 is 3, 3 times 4 is 12, 2 times 3 is 6, 4 times 6 is 24, and 5 times 5 is 25, and 3 times 5 is 15. So we fill that column up. Let's also now do x squared. make sure you get the x variable. So 2 square is 4, 1 square is 1, 3 square is 9, 2 square is 4, 4 square is 16, 5 square is 25, 3 square is 9, so 4 square is 16, 3 square is 9, 4 square is 16, 3 square is 9, 6 square is 36, 5 square is 25, and 5 square again is 25. And let's find the sum. We will add xy, x squared and y squared so we can find the sum. So the sum of x, we add that column, gives you 20. The sum of y, we do that, we add it all up, gives you 30. The sum of xy, and when we sum that, we get 93. The sum of x squared, we sum that, we get 68. And the sum of y squared, we add that up, we get 136. Now let's move to the formula for r, the correlation coefficient. R is n times the sum of x times y, take away the sum of x times the sum of y. All that we're going to put, we are going to divide that, and the denominator will be n times the sum of x squared, take away the sum of x, and when you have the sum of x, then square it all. This is going to be one operation. We're going to put brackets on it, and then another bracket, n times the sum of y squared, and we're going to subtract that. Now let's substitute the values. N is 7, that's how many data points we have. The sum of x, y, it is right here. It's 93, and then we're going to have a subtraction. The sum of x times the sum of y, and those you can find, write the sum of x. Here's the sum of y. Making sure also that we don't forget the subtraction sign. Right, and we keep the parentheses. We're going to divide that, we're going to keep substituting, and the denominator we have n. Right, we have the brackets n, which is 7. The sum of x squared is 68. Take away the sum of x. We'll look in the column, which is 20, and then we square that, and then we close the bracket. Then the new bracket and a 7, the sum of y squared is 136, and subtract that, we find the sum of y, and then we square it and we close the bracket. Now the next step is going to be start multiplying and simplifying this a little bit. So 7 times 93 is going to give you 651. 20 times 30 is going to be 600. Divided by 7 times 68 will give you 476. Subtract the square is going to be 400, and then make sure you put the brackets. Then the next bracket, 7 times 136 will give you 952, and subtract that from 30 square, which 900. So the next step will be 651, take away 600, that is going to give you 51, divided by 476, take away 400, that's going to give you 76. 952 take away 900, that's going to give you 52. Let's rewrite 51 divided by 76 times 52 is going to give you 3.952. Then again, 51 divided by the square root of 3,952, that's going to be 62.8649. And then we do the division and give you 8.11, which is very strong correlation, a strong relationship between x and y. Let us proceed to the Pearson correlation second example. A researcher collected data from 5 participants, participants A and E. Each participant was asked to fill out 2 surveys, which will serve a variable x and y. The first step is to find the products of x and y. To do this, multiply the x and y values in each row. See Figure 3. This gives us a new variable column, x, y. Next, sum the values in each column as seen in Figure 3. Figure 3 finding the products of x and y. Now, simply plug those summed values into the formula for SP to get the new sum of products values. See Figure 4. Figure 4 plugging values into the sum of products SP formula. The next step is to calculate the squared deviations for x and y variables. To do this, find the average of the x and y variables. Figure 5, find the means of x and y. Then subtract the average of x from each score in the x column to find the deviation scorer for x. Do the same for the scores in the y column to find the deviation scores for y. Figure 6, finding the deviation scores of x and y. Next, square each deviation value to find the squared deviation of x and y. Then, sum the squared deviations for x and y to find SSX and SSY. The second topic that we will be discussing is the Spearman rank correlation. The Spearman rank order correlation coefficient, Spearman's correlation for short, is a non-parametric measure of the strength and direction of oscillation that exists between two variables measured on at least an ordinal scale. It is denoted by the symbol Rs or the Greek letter P, pronounced rho. The text is used for either ordinal variables or for continuous data that has failed the assumptions necessary for conducting the Pearson's product moment correlation. So what is monotonic function? To understand Spearman's rank correlation, it is important to understand monotonic function. A monotonic function is one that either never increases or never decreases as its independent variable changes. The image explains three concepts in monotonic function. The first graph explains the monotonically increasing, when the x variables increases and the y variable never decreases. The second graph explains the monotonically decreasing, when the x variable increased but the y variable never decreases. And the third graph explains the non-monotonic, when the x variable increases and the y variable sometimes increases and sometimes decreases. Monotonic relation is less restrictive when compared to a linear relationship that is used in Pearson's coefficient. Although monotonicity is not the ultimate requirement for Spearman correlation coefficient, it will not be meaningful to pursue Spearman's correlation without actually determining the strength and direction of a monotonic relationship. If it was already known that the relationship between the variable is non-monotonic. This is the Spearman correlation formula. Here n equals of data points of the two variables, di is the difference in ranks of the eighth element. The Spearman coefficient P can take a value between +1 to -1 where a p-value of +1 means a perfect accession rank. A p-value of -1 means a perfect negative accession between ranks. Closer the p-value to 0, weaker is the accession between the two ranks. We must be able to rank the data before proceeding with Spearman's rank coefficient of correlation. It is important to observe if increasing one variable, the other variable follows a monotonic function. Here is the example question of Spearman rank correlation. These scores for 9 students in physics and mathematics are as follows. Physics 35, 23, 47, 17, 10, 43, 9, 6, and 28. Mathematics 30, 33, 45, 23, 8, 49, 12, 4, 31. Compute the students' ranks in two subjects and compute the Spearman rank correlation. Step 1. Find the ranks for each individual subject. Order the scores from greatest to smallest. Assign the rank 1 to the highest score, 2 to the next highest, and so on. Step 2. Add a third D to your data. The D is the difference between ranks. For example, the first student's physics rank is 3 and math rank is 5, so the difference is 2 points. In a fourth column, square your D values. Step 3. Sum. Add up all of your D squared values. 4 plus 4 plus 1 plus 0 plus 1 plus 1 plus 1 plus 0 plus 0 is equals 12. You will need this formula. The D squared is just the sum of D squared values. Step 4. Insert the values into the formula. These ranks are not tied, so use the first formula. To compute this, you will get the Spearman rank correlation for this set of data is 0.9. The second example of Spearman's correlation, to calculate a Spearman rank order correlation on data without any ties, we will use the following data. Marks of English 56, 75, 45, 71, 62, 64, 58, 80, 76, 61. Marks of Math 66, 70, 40, 60, 65, 56, 59, 77, 67, and 63. We then complete the following table, where D equals difference between ranks and D squared equals difference squared. We then calculate the following. D squared equals 25 plus 1 plus 9 plus 1 plus 16 plus 1 plus 1 equals 54. We then substitute this into the main equation with the other information as follows. P equals 1 minus 6 times 54 divided by 10, then 10 squared minus 1. P equals 1 minus 2, 324 divided by 990. P equals 1 minus 0.33, P equals 0.67 as N, hence we have a P or RS of 0.67. This indicates a strong positive relationship between the ranks individual obtained in the Maths and English exam. That is, the higher you rank in Math, the higher you rank in English also, and vice versa. Finally, let us discuss the last topic about Cramer's correlation in statistics. Cramer's V, sometimes referred to as Cramer's phi and denoted as P cube, is a measure of association between two nominal variables. Giving a value between 0 and +1, it is based on Pearson's chi-squared statistics and was published by Harold Cramer in 1946. P-cube is the intercorrelation of two discrete variables and may be used with variables having two or more levels. P-cube is a symmetrical measures it does not matter which variable we place in the columns and which in the rows. Also, the order of rows or column does not matter, so p-cube may be used with nominal data types or higher, notably ordered or numerical. Kramer's V may also be applied to goodness of fit chi-squared models. When there is a 1 times k table, in this case r equals 1. In this case, k is taken as the number of optional outcomes and it functions as a measure of tendency towards a single outcome. Kramer's V varies from a zero, corresponding to no association between the variables, to 1, complete association, and can reach 1 only when each variable is completely determined by the other. It may be viewed as the association between two variables as a percentage of their maximum possible variation. P cubed square is the mean square canonical correlation between the variables. In the case of a 2 by 2 contingency table, Kramer's V equal to the absolute value of phi coefficient. Note that as chi-squared values tend to increase with the number of cells, the greater the difference between rows and columns. The more likely p cube will tend to 1 without strong evidence of a meaningful correlation. Kramer's V is calculated, or Kramer's V equals the square root of x divided the n and c minus 1 in r minus 1, where x squared in the chi-square square statistics n is the total sample size, r the numbers of rows, c is the number of columns. Let us take an example of Kramer's correlation. Interpreting Kramer's V for 2 by 3 table. Suppose you want to know if there is an association between eye color and gender, so we survey 50 individuals and obtain the following results. Eye color of the male in blue is 6, green is 8, and brown is 12. For the eye color of female, the blue is 9, green is 8, and 10 in brown. We can use the following code in R to calculate Kramer's V for these two variables. Kramer's V turns out to be 0.1671. Referring to the table above, we can see that a Kramer's V of 0.167 and degrees of freedom equals 1 indicates a small or weak association between eye color and gender. Next example, interpreting Kramer's V for 3 by 3 table. Suppose you want to know if there is an association between eye color and political party preference. So we survey 50 individuals and obtain the following results. Political party preference: Republican blue eye color is 8, the green one is 5, and 6 in brown. For Democrat, blue eye color is 2, green is 8, and 3 in brown. And Independent, the blue color is 4, 6 in green, and 8 in brown. We can use the following code in R to calculate Kramer's V for these two variables. Kramer V turns out to be 0.246. Referring to the table above, we can see that a Kramer's V of 0.246 and degrees of freedom equals 2 indicates a medium or moderate association between eye color and political party preference. And that's the end of my discussion about the topic of Pearson correlation, Spearman-Rank-Brock relation, and Kramer's correlation. Thank you for listening.